Hello, welcome everybody. Thanks for joining this session, for being with us today, and thanks also to GEO Secretariat for providing us with the opportunity of organizing this session. My name is Belén Martín Miguel. I work at the World Meteorological Organization, and I provide support to OOPC, which is the Ocean Observations, Physics and Climate Panel. It's a panel of experts, of physical oceanographers, and this panel, the work of this panel contributes to the objectives of 3 different programs, which are GCOS, GOOS, and WCRP. And these 3 programs are co-organizers of this event. There's a little bit of an echo. I don't know if our colleagues from GEO can help with that.
But I'm not backstage.
Okay. Okay, now I think. Perfect. I think it's going well now, right? Okay, so yes, sorry. I was saying that this is a joint event that is co-organized by 3 different broader programs, GCOS, GOOS, and WCRP. The session is around Earth observations and how critical they are to understand and predict climate change and to adapt to climate change, and also to advocate for a sustained global climate observing system. And for that, we will have the contributions of these 3 programs, providing 3 complementary perspectives through 3 different talks. And we have 3 speakers and 1 moderator that I will introduce in due time. So the session will be like that. We will have these 3 different talks, and then we will have 20 minutes for questions and answers. So I invite you all our audience, to start asking questions. Don't be shy. You have the Q&A section there to leave your questions, and we will get to them at the end of the session. Well, 20 minutes before the session ends. I think yes, I think I'd rather start. Our first speaker is Karina von Schuckmann. She will speak on behalf of the Global Climate Observing System, GCOS. And Karina is an oceanographer. She's based in Toulouse, Mercator Ocean. She works for Mercator Ocean International, and she is one of the experts of OOPC, the panel that I mentioned before. So I'm very pleased that Karina is here with us. She will be talking about the Earth system cycles. She's the lead author of some of the most recent IPCC reports, and she's also member of one of the GCOS task teams around Earth system cycles, precisely. So let's go, Karina. Please, you have the floor. Karina, you need to unmute yourself.
Thank you very much. I apologize. Thank you very much for the introduction. And I have a pleasure today to introduce on the importance of monitoring for understanding Earth system cycles. Presentation which had been put together by myself and Han Dolmon, the chair of the steering committee of GCOS. I would start with the information that the Earth system complexity and the cycles as a starting point. And there are 3 major cycles, including the water cycle, the energy cycle, and the carbon cycle, which all 3 of us transfer and store carbon, water, and heat and as a form of energy in the climate system. So the balance of those Earth system cycles is the most fundamental condition for making planet Earth conducive to sustaining life. So the consequence, there is hence a critical need to continuously observe the Earth system cycle budgets and the inventories, and to understand the mechanisms of change and so that the change in the cycle state can be accurately monitored as they evolve, and so that climate projections can further improve. GCOS monitors the so-called essential climate variables of relevance to the Earth system cycles. For again, the water, energy, and carbon cycle on focus here. And since 2010, GCOS determines how well we can close the cycles of three mentioned one. So the aim is to assess the gaps, white spots, and also potential new essential climate variables. And recently there had been a publication of 3 papers, each for one cycle. So one is on closing the water cycle from observations across scale, one on the heat stored in the Earth system, understanding where does the energy go and how do we understand the land, ocean, atmosphere, carbon cycle. I will start with the energy budget, with the question replying to in this paper, where does the energy go? So the Earth's heat inventory is estimated here by providing information on the heat storage from observations, from in situ and satellite observations, but also models for the different Earth system components, the ocean, the atmosphere, the land, and the cryosphere, starting from the 1960s onwards. The meta results include that over the periods from 71 to 2018, the majority of the heat gain of the global ocean was stored in the ocean, with about 90%, from which the majority is stored in the upper 700 meter depths, significant contribution at intermediate depths between 700 and 2000 meter depths, and about 9% at abyssal ocean. The heat gain over land amounts to 6%, so it's the second largest storage part within the Earth's heat inventory. 4% of heat is available for the melting of grounded and floating ice, and 1% is available for atmospheric warming. So the Earth system heat gain over the period 71 to 2018 was estimated to 358 zetajoules, and which is equivalent to a global heating rate, being the energy balance out of balance of about 0.5 watt per meter square. What we have further learned is that the Earth's energy imbalance is not only continuing, so it's also that it is increasing. Over the past decade, there had been almost a doubling of the amount of decicaled energy at the top of the atmosphere. So understanding the heat gain of the Earth system is fundamental to understanding how this affects warming and ocean, atmosphere, and land, and is the most critical number defining prospects for continued global warming. Then also there had been information provided on the paper on the global water stocks and the fluxes. So there had been long-term water cycle monitoring and has greatly advanced in the past, but there are many observational gaps which are still needed to be overcome, aiming to close the water budget, to understand the state and also the change and the inventory, and to enable a comprehensive and consistent assessments across the scales. So the estimates have been provided here for both for the storage components, but also for the fluxes on how water is transferred through the different Earth system components. And this paper publication has further provided specific recommendations on the water cycle assessment. First, on the trends in the water cycle components that can only be observed with great uncertainty, or many due to insufficient length and homogeneity. There's an advanced closure of the water cycle, which is required improved model data synthesis capabilities, particularly at regional to local scale, and also on the definition of future observation system should consider following a more holistic approach and observe water cycle component as part of their global cycle and assess its variability in conjunction with the energy and carbon cycles. Now coming to the carbon cycle, in terms of first the international assessment on the anthropogenic perturbations on the natural taking place on the natural cycle. So the perturbation of the global carbon cycle caused by anthropogenic activities has been estimated and as a global average for the decade 2010 to 2019 as part of the Global Carbon Project. And the quantification of 5 major components have been considered here of this global carbon budget and their uncertainties, including the fossil fuel carbon emissions, emission from land use change, atmospheric CO2 concentration, CO2 uptake by the ocean, and CO2 uptake by terrestrial biosphere. And so the differences of these estimates of the total emissions and the estimated change in the atmosphere, ocean, and terrestrial biosphere provide the carbon budget imbalance. As part of GECO's initiative, there is this assessment on the relative errors in the annual global carbon project budgets. And this, I will particularly point here on the uncertainties, on the largest uncertainties on the land component, and we will have further insight on the ocean component in the preceding talk. So the discrepancy in observation of the carbon cycle between sources and SIGs reflects the overall uncertainty of observation and is 0.5 gigatons carbon emission per year, or 3%, which is representing 3% of the global emissions. So in terms of the uncertainty is caused by the uncertainty in both the land sink and the land use change, which in turn hampers our ability to detect interannual changes, and improvements are really needed at this edge. The likelihood is high that substantial climate carbon feedbacks will occur during the century, and so any upward change in the atmospheric fraction or the reduction in the sink capacity will decrease the allowable fossil carbon that can still be burned. So the maintenance and expansion of both in situ and satellite observations of both the flux parts and also the stocks, carbon stocks, are required to accurately observe and monitor the carbon budget change and also to reduce the uncertainties. Last, other take-home messages with particular focus on the water and energy and its implications for the observing systems. So since about 90% of the excess energy goes into the ocean, it is critically important to sustain, extend an integrated ocean observing system, such as the Argo component and the satellite components. And the turbulent fluxes and of latent and sensible heat are one of the critical uncertainties which need urgent improvements. And then also to be able to better close the global hydrological budget, a new terrestrial essential climate variable, the terrestrial total water storage, has been agreed that integrates over the land hydrological cycle and can be observed from space over large areas, such as from GRACE and also GRACE follow-on, and links directly to one of the more uncertain essential climate variables, evaporation. And the melting glaciers contributes about 50% of total sea level rise, and so continuous monitoring, satellite and in situ, of the large ice sheets and glacier remain therefore critically important. Thank you very much.
Thanks very much, Karina, for this very comprehensive and yet extremely efficient talk. I encourage everybody, if you, because it's been a lot of information, so if you would like that Karina developed part of what he's been saying later on, please just write your questions in the Q&A. And now we will deep a little bit into the ocean with Torste Tanua, who is a senior researcher, also an oceanographer working in GeoMar in Germany. And he is also the co-chair of our second program, organizing program, GOOS, the Global Ocean Observing System. So Torste, your turn, thanks.
So thank you very much, Belen, for that. And I hope you can see my screen now. So yeah, I'm co-chair of the Global Ocean Observing System, GOOS. And GOOS is a permanent program to function as a long-term coordination effort. So this is for sustained ocean observing, serving society needs for climate, operational services, and for ocean health. And I will, of course, now focus on the operational service part of that. One part of GOOS is called Ocean Ops. GOOS has many different parts. And this particular component of GOOS is monitoring the status and the impact of the ocean observing system. And you see this world map with the ocean observing things highlighted here as different colored dots and lines. It looks like a lot of observing units in the ocean. it's not really, because the ocean is large and many of these lines are repeated on, every 10 years and so on. But that resource we have in ocean ops is really valuable for us to understand where our observational assets for in situ observations really are and how we're doing on the observing system. And Karina also already mentioned the essential climate variables, and the ones for the ocean are listed here. There are quite a few of them. In GOOS, we define something we call essential ocean variables. There are a few more. But for this particular talk, I will focus just on two variables that I think are really key for climate and ocean, and it's the one on interior ocean temperature and on inorganic carbon. So you know that these units are something that we cannot observe from space. They are helpful to have remote sensing observations to extrapolate and understand, but you really need to have in situ observing elements for that. So in GOOS, we're trying to link the ocean carbon observations to climate targets, and we are working in GOOS along a value chain that goes from input to processes, outputs, which are data and impacts, and there is a curvy snake here going back, and we're trying to evaluate the impact and efficiency of the whole observing system. So GOOS itself is really focused or centered around the processes of deployment of observational units. If you're interested, you can really read our strategy. 2030 strategy was published a couple of years ago in the website. So as Karina just explained to us, the ocean really holds around 90% of the excess heat. So if you want to understand climate change and global warming, we really need to understand ocean heat. And on this graph from Karina's paper last year, you can see how the blue part of that curve is the ocean, is 90%. And more interesting in this case, I think that you can see that the dashed lines here, the uncertainty of those estimates, how that really narrows down. And the reason it has narrowed down is almost entirely due to the Argo program. These profiling floats that are, we have about 4,000 of them right now in the ocean. And they are programmed to every 10 days go up and down and make a temperature and salinity profile of the ocean. To the lower right here, you see a vision for an extended Argo program. And the red dots there are the core floats. We also have deep floats, remembering that the core floats only measure half of the ocean, the top 2,000 meters. The deep floats are designed to measure that deeper part of the ocean. And the green part dots here are really BDC, biogeochemical Argo, that measures things like oxygen and pH, bringing me to the next part of my presentation here. I talk about the carbon cycle. And you saw this picture from Karina's talk, the one to the right here. I just like to point out the magnitude of the stocks here. So in the ocean, the stock of inorganic carbon is something in the order of 37,000 gigatons of carbon. And if you compare that to the stock of the land-based vegetation is 450, and all the carbon in soils is 1,700. It's really small compared to the big stock in the ocean. So the ocean is really a driver of the global carbon budget. And in the climate targets, we really care about that blue dot here, the 875 gigatons of carbon in the atmosphere. But how that evolves will, of course, determine our climate, but the ocean will drive how that carbon in the atmosphere really evolves. To the left, you see a waterfall diagram on where the carbon has gone, the one that we have emitted through different burning of fossil fuel, land use change. And the main message here, I think, is that the ocean has taken up around 40% of the cumulative fossil fuel emissions. And without the ocean, we would have around about 80 ppms more carbon dioxide in the atmosphere, and thus much more of global warming. So where does the carbon go? To the left here, you see a complicated graphics with the Antarctic in the center and the 3 different oceans, looking at the vertical section. And the redder, the more anthropogenic carbon we have there, that's been taken up in a particular time period here, the last 20 years or so. You see most of the carbon is in the upper 500 meters. We see particularly much in the Atlantic Ocean. To the right, you can see 3 global pictures. The first one is the mean partial pressure of a carbon dioxide, and that translates directly to the flux, which is in the middle panel. Red is carbon dioxide going from the ocean to the atmosphere, and blue is the other way around. And it's the net between the red and the blue here that really determines the carbon flux into the ocean on an annual basis. The lower panel shows you where the carbon is stored in the interior, and most of it is in the North Atlantic, but a lot of it is stored in the Southern Ocean. So what do we do to determine the carbon cycle in the ocean? Basically, we look at 2 different components. We look at the surface, and that is organized by a network called SOCONET, and the data product there is called SOCAT. And we also look at interior ocean carbon, which is observed by research vessels, and the data product we have here is called GLODAP. Both of these products are updated on an annual basis, but are unfortunately very fragile in terms of sustained funding. Karina also showed you this graph here, and what I really would like to say here is that we can constrain the carbon budget and stocks and fluxes for the atmosphere and for fossil fuel emissions pretty well. For the land use and land sink, it's more difficult. We are ending up with uncertainties in the range of 40 to 50%, whereas in the ocean we are now landing at 20 to 30%. And I think, and I know for sure that we can do much better than that. In the global climate target, the ocean is missing. It's really not taking into full account that the ocean sink of carbon dioxide will change with time. We don't exactly know how it will change. I think we can expect surprises, but we don't have the observing system to really detect those surprises. So I really would like us to put the ocean back on the map. And we need the ocean to be able to assess the efficiency of mitigation efforts and to support any adaptation efforts. The ocean community know how to do that. If you look at this pyramid here, you see the different observing elements in the bottom row. And I added a couple of exciting new observing platforms to the left here. So these are robots, either sailing or using wave power to apply the surface of the ocean, or this biogeochemical Argo float that can measure carbon at the top 2,000 meters. All the observations are synthesized in these 2 data products I just talked about, and that leads into the science of doing assimilations and forecasts and assessments of the carbon stock and carbon sink, leading to assessments and leading to the process of policymakers supported by GECOS and GOOS. The Global Ocean Observing System GOOS are working along the framework for ocean observing. That's guiding how we can design an observing system. We also have the integrated ocean carbon research work. Is a brochure, as a paper that was published by IOC, the Intergovernmental Ocean Commission, just recently. And by that, I would thank you, and I would leave you with this vision and mission of GOOS and the 11 strategic objectives from the 2030 strategy. And let us come together and try to observe ocean sufficiently well to understand climate. Thank you.
Thanks, Torsten. Thanks very much. And thanks for providing this closer look at one part of the carbon cycle. And now we will go to our third speaker, who is Patrick Kemba, who will be speaking on behalf of WCRP. He is also an oceanographer, but a computational oceanographer, so that it is clear to us that he doesn't go on a cruise that often. And this time, he's a professor in the University of Texas, Austin. And this time I will share the screen for him. Patrick, I hope now, I think should be there. Mm-hmm. Perfect. So now I will just mute my microphone and I would.
Well, yeah, thank you very much, Belen. And yeah, so my name is Patrick Heimbach. I'm speaking on behalf of a recently, meaning a year ago, formed a so-called WCRP Lighthouse Activity on Explaining and Predicting Earth System Change, or EPESC. The co-chairs of that Lighthouse activity actually are Rowan Sutton at Reading and Kirsten Findel at NOAA GFDL. Next slide, please. So the rationale of this Lighthouse activity is the recognition that the signal of anthropogenic climate change is emerging progressively from the background of natural variability, and our community really has been excited that by this year's Nobel Prize that basically, sorry, I just need to change location here. The Nobel Prize on the subject of detection and attribution, and the emergence is seen on multi-annual and longer timescales, and is becoming ever more apparent as the smaller scales and also locally. So, but the important thing here for our purpose here is that the capability for quantitatively explaining and predicting such changes on these timescales, meaning interannual and decadal timescales, really remains exceedingly limited. And an example of this over the last decade has been the hiatus. And we're particularly poor at explaining these changes in the dynamical variance, and both in atmosphere, ocean circulation changes. So we need to really make progress here. Next slide, please. So the objective then of this Lighthouse activity is to design and take major steps towards the delivery of an integrated capability for quantitative observing, explanation, and early warning and prediction of Earth system changes, both on global scales, but also on regional scales, and really with time scales that are multi-annual to decadal. Example of features that we seek to target here are the explaining and potentially predicting new processes like a hiatus, if it were to come again, interdecadal Pacific oscillation phases, changes in AMOC on multi-annual timescales, rapid regional ocean warming, some marine heat waves, and related features. All of these we can beginning to monitor them, but we have so far limited predictive capability. And the reason for doing this is again that these provide the baseline for actually then explaining hazards and extreme events, which are again key for policymaker, for risk assessment, and for adaptation. Next slide, please. So our Lighthouse activity has been structured into 3 themes. First theme is monitoring, modeling, and modeling the Earth system change. Here, the observation and modeling requirements are to monitor, explain, and predict Earth system changes. And then one gap that we're recognizing is the convergence between the climate modeling and the Earth system data assimilation community. And I'm going to talk about this a little bit more. We have a second theme, and on the second theme, there just has been a workshop in October, and that is the integrated attribution, prediction, and projection and early warning. So here, what we want to do is a quantitative process-based attribution of Earth system changes, integrated attribution, prediction, and projection, building on another WCRP grand challenge on near-term climate prediction, including the signal-to-noise paradox. And then they contribute to the WMO state of the global climate, an annual to decadal climate updates, and then early warning of major changes. So then the third theme is that within the lighthouse activity is the assessment of current and future hazards. So this is here really more about extreme events and hazards. So we focus on classes of events rather than on individual events. So the idea here is, again, do we see patterns of events that we can maybe better understand and predict? Then understanding of the natural anthropogenic drivers of changing hazards in different regions and extending the event attribution methodologies. Next slide, please. The lighthouse activity on explaining, predicting, and Earth system changes lives sort of within other lighthouse activities that also have been spun up. So there's a couple of those lighthouse activity that have been proposed and agreed upon a year ago, and there are clear overlaps between all of these lighthouse activities, and therefore there's a real strong opportunity for collaboration and learning for those. The other lighthouse activities are shown here. One is safe landing climates. A second one is on the digital Earths. And then the third one is on climate risks. So this is really the risk attribution. And of course, the explaining and predicting Earth system change lives sort of at a space that, at least that's how we see it, as really the fundamental understanding, monitoring, simulation to then inform some of these other lighthouse activities. Potentially, for what we're talking about here, namely the interconnection between GOOS and GCOS, the digital Earth is one that's certainly of particular interest also. Next slide, please. Yeah, next.
Sorry, yes, it's not, what's a second now, sorry.
So I'm going to go a bit more into detail for the theme one, because the theme one is really closest to the topic that we're discussing about here. And the theme one has two major building blocks. The one is monitoring and observing Earth system change, and of course modeling Earth system change. The first clear thing that we propose here is that these two should be considered jointly, and there should be a tighter link be made between the two. The possible partners of this lighthouse activities, that again is just really spinning up now, is of course another core program of WCRP, which is also a new program. It's called Models and Data. That group has also just been formed. Then, as I've mentioned, the lighthouse activity of digital twin Earths, and then the WMO data and modeling committees, and then obviously both GCOS and GOOS. Next slide, please. So the identified gaps for this theme one, there's a number of them. So the first one is that we recognize that there are persistent biases in model simulations. Model error accumulation over time remains unclear. And this has been clear. There are some of these persistent biases, they have been persistent over several generations of IPCC or CMIP generations. And so we really want to see, what are those gaps, how we can overcome those gaps, how can we progress here. The second one is arguably at least, the underutilization of the diverse optional data that we have from GCOS and GOOS for comprehensive climate model calibration and also model initialization, which we think that if we were using those data streams more comprehensively and more effectively, might actually alleviate some of these climate modeling biases. A third gap is there appears to be potentially, again, arguably, a disconnect between Earth system reanalysis or data assimilation on the one end, and then the climate modeling community on the other hand. And so here, what we're looking for is that we think that that some of the efforts of data assimilation and approaches are not necessarily targeting major needs, for example, initial condition estimation versus model parameter calibration, which are both, of course, very important, but where we think there is sort of gaps in how those are utilized. Next slide, please. The fourth gap is the sparse observational sampling that persists, of course, in many parts of the Earth system, in particular of the ocean. And this is perhaps why a lot of, 3 of the oceanographers are present here in the session, which warrants extra care in using the observations that do exist in the context of the modeling. And also an opportunity potentially here for a better, trying to design observing systems for climate that really takes the ocean and the need of ocean observations better into account. And finally, and related, so at the present time, we only have simple ad hoc approaches for dealing with the combined stream of these diverse sources of uncertainties from the observations of the model, again, in basically producing some derived quantities of the climate and ocean state. Next slide, please. So we come to the proposed activities, and the main thing that we think would be useful to do is to select a small number of recent climate anomalies that have occurred over the past 1 or 2 decades, and the hiatus has been mentioned as a good example, but there are other very compelling examples, to develop process studies to understand a couple of things. So the first one is to ask the questions, how early were these events that we are interested in recognized as such? How well are these events monitored by the different elements of GCOS and GOOS? And I keep highlighting GOOS here, not just GCOS, GOOS actually. And we did this prior to the session. We actually mentioned both of these efforts. And part of the reason being is that we were highlighting the ocean as particularly sparsely sampled compared to the atmosphere. And also, as been shown by our previous speakers here, that it's the ocean sort of as a major flywheel of the in memory of the climate system. So third one is how well are some of the underlying metrics that we're interested in, how well are these actually constrained, right? So regional versus global heat content anomalies, global mean value, and where we have to recognize that the global mean values are really small residuals of large regional variations that are on a, let's say, seasonal timescale can be exceed the residual global mean by easily 2 orders of magnitude. Next slide, please. Then to continue with the proposed activities, do the observations that we have and enable mechanistic understanding of some of these anomalies, how they evolve, and how, for example, is the observational coverage of upstream or back in time processes that lead to these events, if we have the dynamical correct, how well are those actually monitored, not just the events themselves, but their potential precursors. And then what methods could further inform observing system design in a more quantitative manner, and that where basically such design methods could help guide observing system strategies to constrain some of these quantities. And then finally, the performance of models and data assimilation systems are basically need to be assessed. And then next slide. And so some of the final thoughts that I have is that obviously for this session, the observing networks under GCOS and GOOS play a major role in this lighthouse activity, and so we should have very strong links between those. There is a real need, and Toste had this in his pyramid of the different elements of global observing systems, for developing and maturing a coupled Earth system data assimilation to really combine the 2 knowledge reservoirs that we have from the observations and what we know in terms of physics as encapsulated in the models. We should incorporate ideas and approaches for coupled Earth system data assimilation for more comprehensive Earth system and climate model calibration and initialization. And I think it's coming more and more to the recognition in the community. And then finally, the uncertainty quantification is a particularly challenging issue. And again, here, the question is, how can we basically improve more robust uncertainty estimates that come from the different sources of uncertainty, which are the observations, the modeling systems, and the synthesis systems, where we have to make progress. And with that, I finish. Happy to take questions.
Thanks. I'm afraid we've run a little bit over time. So now I will go straight and I will invite Emma to join us to moderate the question and answer part of this session. Emma is an oceanographer also, but in addition to her expertise as physical oceanographer, she has also rich experience in business and strategic development, and she has been responsible for developing GOOS 2030 strategy. She's a program officer in GOOS, in fact. So Emma, now it's your turn and your difficult task to moderate in just 10 minutes.
Right. Okay. So I'd encourage people to put their questions into the chat because, or indeed the question and answer section. We've had a very interesting answer from Karina about the energy cycle, and so perhaps I would ask a follow-on question, both to Tosta and to Karina, and ask perhaps on the carbon cycle and the carbon observing area. Where would you best target placing the observations if we wanted to prioritize that, let's say next year, which is pretty close now? So I perhaps ask Karina first and then move to Tosta.
Maybe Tosta is a better place to start first, and I will complement.
Okay.
Okay, Emma. So that's a good question. I showed a couple of maps on where the fluxes and the interior storage of carbon is particularly high. And those areas are North Atlantic and the Southern Ocean, particularly the Indian Ocean and Atlantic Ocean part of the Southern Ocean. So whereas we have some observations and some understanding of the North Atlantic, that is probably an area where we can expect big changes in the future. So there's importance to start there. The Southern Ocean is interesting because it's a little bit of a white map in terms of carbon observations because it's so difficult to get there, particularly in the winter. So it's hard to prioritize between these two, but those are the geographic areas I would focus on if I had some money in my pocket to start. Thank you.
Great, thanks, Tosta. And a follow-up question would be, you have the surface maps and also the deep observations are important in both these areas, I take it.
Yes, it is a combination of both. The surface observations are good to understand variability on annual and sub-annual scales, whereas the interior ocean estimates requires more like a 10-year time period to see changes. It really works as a control mechanism for those surface fluxes. So there's different time scales that they operate on.
Excellent, thank you. So Karina?
Yes, thank you. Because there's coming up often this question on prioritization, I think I would like to flag on that it's also very important to identify the question you want to reply to in order to then perform with the prioritization. So in terms of the cycles, we'll quickly start with the energy cycle and then go again to the carbon cycle. I think prioritizations could be organized maybe on two big questions. So the first would be on the storage part, how much heat is stored, how much carbon is stored, and then on understanding also the state and how all those cycles are out of balance. And the second question could be ordered around the changes of those out of balance situation or states. And so I think for both there are different answers. So for the storage part, I mean, these are the storage components. We have heard from Tosta, prioritization, for example, for carbon. And so particular, for example, as you mentioned, the Southern Ocean is there, the critical area has been identified of one of the reasons maybe explaining lacking information on uncertainties in terms of understanding decadal scale change. And also the fluxes are important. So for all the cycles, so that's my point on the changes, because there is still uncertainties, I think, for all of the Earth system cycles, and also that you would need to understand how this energy, heat, and carbon energy and water, is transferred between the different Earth system components. And I think that would help us in order to further understand the changes and the processes of those changes.
Excellent, thank you very much. And I also noted that sort of in your answer in the chat on the energy cycle and also in Toster's answer, we're seeing some of the same parts of the global ocean coming up as hotspots to prioritize for these observations. So moving away from directly onto observations, perhaps to the observing modeling interface, sort of looking at moving down the value chain, I noted in Patrick's presentation that there were quite a lot of mentions of perhaps engaging and creating links between WCRP, GCOS and GOOS, but also perhaps between the observing community and the modeling community, be that on, let's say, on a simulation. I think you mentioned getting all observations, more diverse range of observations in, and a couple of other areas. So perhaps my thoughts as we're together with modeling and the observing community, where would you place the priorities for that interaction, and how would you help foster the things you see would be needed? First to Patrick, and then anybody else who'd like to respond.
Yeah, no, that's a great question, and I think the methods on how we are thinking of for example, calibrating climate models, I think they have a very strong impact on climate models, for example, persistent biases, and we're seeing this being increasingly recognized with the recent increase in projects that try to use novel methods, either machine learning or inverse methods, in order to really have a much better ingestion of these observations, in order to reduce some of the things that we don't know and that have uncertainties in climate models. Climate models remain in the foreseeable future fairly coarsely resolved. They will have to rely on parameterizations, be it in the ocean, where we're still relying on parameterizing the non-resolved mesoscale eddy field, or in the atmosphere, where cloud parameterization is, of course, a big topic. These processes have uncertain parameters where we can and we should use the observations to actually see whether we can actually formally improve those calibration, refine those numbers, and it is here that we think that the observations are just not used in a way, or they are used to validate models, but then to try to inform, for example, constraint calibrations requires new thinking in terms of the modeling algorithms and methodologies on how we can do this. And so the of course a related topic here is the access of the data, but I think for the type of observations that we need, I don't think that is the main issue. We have really good access to the suite of Argo data, the suite of the range of satellite observations, both in the US through NASA, NOAA, in Europe through Copernicus, and it really is now the developing algorithms to really use those data for a more consistent model calibration. It's an aspect that maybe has been overlooked, but that is now beginning to receive improved recognition through let's say new methodologies that we find that we're deploying.
Thank you, Patrick. That's really interesting. Toster, did you want to add something in? You have your microphone.
No, I wanted to highlight two things that I heard from Patrick in that interface. And one thing was the support from the model community on observation design, observing system design, which I think we could work much more together on to maximize the bang of the buck when we put something in the water. I think that is a big thing. I was a bit surprised to hear from you that you don't think that access to data is the big problem. And I think you're thinking about the way the Argo is working. I think we have a few other observing systems in place where maybe the data is not that easily accessible. And I think if we can work together on improving the utility, you said before that the data that we have, the observational data, is underutilized. So how can we work together to utilize this data better? And I see a lot of very promising approaches in advances in data assimilation. So I think data assimilation is clear. You need observation in the models. So I think that is an interface where we can take big strides, I think, and make a lot of progress. And it's in a way, it's a low-hanging fruit, even though that doesn't mean that it's not easy. So I think these are the two things that stand out for me: data assimilation and system design.
Yeah, if I can.
So with adding to, sorry, when Patrick mentioned new algorithms and new areas, I was thinking of the Ocean Decade and some of the projects that are sort of put forward around co-design in that area. And I think that this is possibly a good area. Anyway, sorry, Patrick.
Yeah, no, I agree that the UN Decade provides some really potential opportunities to make some progress in a way that we're maybe haven't made so far. And I wanted to, really reinforce Tosta's comment on the co-design and observing system design. If done well, it's actually mutually informative, right? So there is a perception that potentially models are not good enough to design observing system, but through this iterative process of engaging with observationists and recognizing that maybe the information has shortcomings, will in turn improve the model component, and to then in the next iteration say, okay, well, here is how we can make progress. So I see this as a two-way iterative process where there is sort of an incomplete observing system, there are underperforming models, and through this joint co-designing and then iterating and improving, there should be some real progress made.
Great. So perhaps we have time for just one more question, if that would be allowed, because I'd quite like to pick up, if we move down the value chain a little bit more towards the end users and how they're going to get hold of this information that we know is required to work on climate adaptation and mitigation and understand government policy. And I saw in your slides, Patrick, you were talking about the digital twins of the ocean, which are, again, perhaps related to some decade project areas. But what are there specific areas where, again, we really need to focus our attention on? And this would be a question to all the panelists, where there's a big opportunity to improve the uptake of this information. So I don't know if you want to start, Patrick, with the digital twins.
Sure, I can give this a crack. So the digital twin is it's an emergent concept, and different people still have different sort of mental models about what digital twins actually are. But in Europe, I think the concept is somewhat further developed through Destination Earth. I think especially for the ocean, there is a real opportunity to connect between the physical state of the ocean and the climate system, where we have more mature modeling and data assimilation systems, and then potentially, ecosystem biological aspects, where this is, of course, where there could be potential strong impacts, right? So changing in the ocean state on the ocean biodiversity, on ecosystem, changes in fish population and the blue economy in a broad sense. And so the digital twin concept may be a way on how we connect both the monitoring of the physical state of the climate and the projection capabilities that are maybe more mature on let's say the OOPC side of things, and then connect this in a more consistent or in a more comprehensive manner with the ocean biology that we're actually all concerned about ultimately, right? So we're concerned about climate change because we're worried about life on the planet, and especially life in the ocean and how it may change. So that is one. I mean, it's a very high level, but without going into details of what digital twins are, I think there could be some real progress made in developing those capabilities.
Great, thank you, Patrick. And I see there's some suggestions also for us as various groups to engage more strongly with the GEO working group in products and areas. Tosta.
So just responding to your question on how we can connect with end users better, I think we need to be better at communicating basic climate science to policymakers and to the general audience. IPCC is a great product, no question about it, but very few people will read all the 4,000 pages. And even if you read a summary for policymaker, you will have a hard time as a non-scientist to understand the graphics there and digest the messages. I think even for policymakers, I'm not saying that policymakers don't understand graphics, but it's something that we as a scientist should work on to communicate the basic concept better to get that message through. That would be a service to the end users to communicate that better. It's a difficult question, it's difficult task to do it, but I think it's our duty to make a good effort at it. Taking down the complicated physical process described in IPCC to a digestible format for the general public. Thank you.
Great, thank you, Tostra, and I would have to agree with that. And so, some good suggestions in terms of communications, perhaps looking to the future. Melody in the chat has suggested that the digital twins is like building a cathedral, so it's going to take a while. So we need to work with Geo also in the meantime in getting the products as well as the communications together. So I think we have to wrap it up there for the questions. So thank you for the discussion in the chat and putting those ideas forward. It's really helpful. And thank you to all the speakers for a really interesting, but also I think, interconnected view of the need for global climate observations. And I pass back to Belen to close. Thank you.
Well, yes, in fact, there's nothing more from my side to add, but to stay with these final messages. Thanks, Emma, and the rest of the speakers, and thanks, Geo, for organizing this Geo Week, and also, of course, thanks to the attendees. And see you soon. I hope in another joint event like this one. But after this experience, next time we need a little bit more of time. Okay, thanks.
Thank you. Bye.
Bye-bye.